everyone, welcome to discussion 9 for CS61B. Today we're going to be talking about binary trees. So let's get into some content review. First of all, let's review what a tree is. So basically trees are these structures that are kind of like linked lists in a way, except instead of pointing to just one object, they can point to multiple. So trees have to follow a few basic rules. If there are n nodes, then there are n minus 1 edges. So in this example down here, you see there's 1, 2, 3, 4, 5 nodes and 4 edges between them. There is also exactly one path from every node to every other node. So if I wanted to get from this node over here over to this node, I would have to go up and then down and then down. There's no other way to get there. It's the only path. And those two rules combined ends up meaning that trees are fully connected and they contain no cycles. So what does that mean? That means that every single node in this tree is connected to every other node. You can find a path and there are no cycles. So there's only one path from every node to every other node. Some terminology that might be useful is that a parent node is a node that points toward a child node. So this is the parent of this and this is the child of that. The root node of a tree is a node with no parent nodes. A tree only has one root because it's fully connected. A leaf, on the other hand, is a node with no child nodes. There can be many leaves in a tree. So we want to get through these trees in order to do things like search. And so we have a couple different ways of doing that. The first is called a breadth-first traversal, where we visit nodes based off of their distance to the source. So in this example, let's say that A is our source. So we visit A first because A is 0 away from itself, and then we visit B and C because those are 1 away from A, and then we visit D and E because those are 2 away from A. BFS is usually done using a queue. And another way of calling this is level order, because as you can see, we're going level by level through the tree. Now, depth-first traversal is another way of traversing the tree, and there's actually 3 different ways of doing depth-first traversal. So pre-order traversals visit the parent node before visiting the child node. So in this case, we start over here, we visit A before we visit either of its children, then we visit its left child, and we visit it before we visit either of its children, and then we visit its left child and its right child, and then when we're done with this entire left subtree, then we go over to the right subtree. It's depth-first traversal because we go all the way down, and then once we hit a leaf, we go up by 1 level, and then we go all the way down until we're out of child nodes, and then we go up 2 levels, and etc., until we've done the whole tree. So we don't visit the right subtree until we visited everything in the left subtree. In an in-order traversal, we visit the left child, and then the parent, and then the right child. So in this case, we don't visit this node yet. We first go to its left child. Same here. So our first node that we actually visit is this leftmost node in the tree, which is the bottom left node. Once we visited that, then we can visit its parent because we finished this entire left subtree, and then we visit B, and then we can visit its right child, which is C. And once we've done this whole left subtree over here, we can finally visit D up here, and then visit E. And then post-order traversals, we visit the child nodes before visiting the parent nodes. So in this case, we visit the left child and then the right child and then the parent. So we go down, down, we visit the left child, we visit the right child, and now once both these subtrees are done, we visit the parent. And now that this whole left subtree is done, we visit the right subtree and then we visit the parent. Pre-order and post-order traversals can be done on any tree. In-order traversals can only be done on binary trees because they do rely on the idea of having a left child and a right child. It doesn't really make sense once you have more children than that. So another thing that's pretty useful to talk about is game trees. So game trees are going to be super important for project 2. The basic idea behind game trees, or min-max trees, is that they allow us to showcase the outcomes of a 2-player game where one person is trying to maximize the total score and the other person is trying to minimize the total score. So you can kind of imagine that this is the player 1, they're acting as a maximizer. Player 2 is acting as a minimizer. So basically, given all of these options, player 2 will choose the minimizer between these and the minimizer between these. So in this case, 2 goes up and 1 goes up. And then player 1 will choose the maximum between these two options, which is 2. So game trees are basically just, you just go through, you take either the maximum or minimum value depending on which level you're at. Where they get a little bit complicated is something called alpha-beta pruning. So this tree is relatively small, so calculating all of this doesn't take too much effort. However, if you look at something like what you're going to do for project 2, you'll see that game trees can become massive very quickly because the size of a tree grows exponentially as you add more levels. So if you want to have a good game tree where you see a lot of options, then we also would benefit from having a way to reduce the number of those options that we actually have to manually calculate. So alpha-beta pruning allows us to reduce the number of nodes we need to visit by determining the best possible move for player 1 using this sort of system that we have. And the basic idea behind this system is, let's say we're in this node right here, right? So we've already looked at this node. We've already seen that this subtree returns a 2 for this minimizer node. And we know that this node right here is 1, so that's what we're going to have here. We haven't looked down this path yet. Well, this node is going to maximize, right? Which means that it's going to take the maximum value between this minimizer node and this minimizer node. Now, if this minimizer node, we know it's going to return a 2, and this minimizer node, we know it's going to return a value that is less than or equal to 1, is there any world in which we would actually end up returning this node all the way to our maximizer? No, right? Because whatever this node is going to return is going to be a higher number than this node. And that's all this represents. Once we know that fact, we know there's no point in looking down this subtree because there's no value that could be there that would both be a smaller number than 1 and a bigger number than 2. And that's represented by these alpha-beta values. The way we find these alpha-beta values is we just put down the smallest value. So alpha is going to be the value by the largest maximizer on the path to the root, and beta is going to be the smallest minimizer value on the path to the root. And again, this is a little confusing because we're just going over this briefly. If you want the actual algorithm, that's on the lecture slides, and we'll also do an example later in this worksheet that I think will be a better explanation. I think doing it is the best way to get through these things. Okay, let's go through the worksheet. So first of all, let's do the DFS pre-order, DFS in order, DFS post-order, and BFS traversal for this BST. So I'll give you a chance to think about it, and then we'll go over the solution together. Okay, welcome back. Let's go over this. So first of all, let's do the DFS pre-order. So if you remember in this one, we are going to visit ourselves and then our children. So here we visit 10 first because that is the root, and then we visit its left subtree. So then we visit 3 next, and then we visit its left node, which is 1, and then once we're done with this, there's no children here, we go back up and we visit its right child, which gives us 7, and now this whole left subtree is done, so we're going to go back up and visit the right subtree. Now we're going to visit 12, and then 13, and then 15, because we visit ourselves and then our children. That gives us 10, 3, 1, 7, 12, 13, 15. For DFS in order, we're going to visit the left subtree and then ourselves and then the right subtree. So in this case, before we visit 10, we're going to go to the left side. Before we visit 3, we're going to go to the left side. And now 1 has no left child. So all we have to do is visit 1. And it also has no right child. So there's nothing to do there. We're going to go up to its parent. And now we can finally visit 3 because its entire left child has been visited. And now we can visit its right child, which is 7. So we get 1, 3, 7. Now again, this whole left subtree has been visited, so we're ready to finally visit the parent, which gives us 10. And then we can visit its right child / right subtree. Now again, 12 doesn't actually have a left child, so we're just going to visit 12. And now that we're done visiting the node, we can visit its right children. 13 has the same problem of not having a left subtree to visit first, so we just visit 13 outright. And then we visit 15, and that takes us through our entire tree. So the final DFS in order is 1, 3, 7, 10, 12, 13, 15, which if you notice is in order because this is a binary search tree. Now let's do post order. So for post order, we visit both of our children, left and then right, and then ourselves. So in this case, we're going to first visit the left subchild, and then again visit the left child. So we're going to get 1 first, and then before we visit this parent node, we're going to visit its right child, which means that we're going to visit 7. And then when we're done with that, we're going to visit 3. So now that we visited this whole left sub tree, we're going to finally go over to the right subtree before we go to the parent. Before we do 12, we want to visit both of its children. There is no left child, so we go straight to the right child. Same thing for 13, there's no left child, so we're going to visit its right child. That means 15 is the next number on our list, and now that we've visited both of 13's children, we're ready to visit 13. And now that we've visited both of 12's children, we're ready to visit 12. And now we've finally visited both of 10's children, so we are ready to visit 10. So our final post-order traversal is 1, 7, 3, 15, 13, 12, 10. Lastly, let's do our BFS level order. So here we're just gonna go level by level from left to right. So 10 is 0 away from itself, so that's gonna be the first thing that we visit. Next, we have 3 and 12, which are both 1 away. We're just going from left to right because that's how we're breaking ties in this case. So 3 and then 12, and then we're gonna visit 3's children and then 12's children. So 1, 7, and then 13. And then we're going to visit the nodes that are 3 away from that root, which is 15. So in the end, we get 10, 3, 12, 1, 7, 13, 15. Just going level by level through the tree. Okay, so let's talk about, is this a BST? So in this instance, we're given a function that allegedly will tell you whether or not something is a BST. However, it is broken. So I will give you a chance to try to come up with a tree that fails when we try to call broken is BST on it. So an example of a tree that is not a BST but is considered a BST by this function. So I'll give you a chance to think about it and then we'll go over it together. Okay, let's go over it together. So an example of a tree that this fails on is this one. So why is that? Now, if you recall, for a BST, everything that is to the left of this root node has to be less, not just its immediate child, but all of it. And the reason for that is if we were to search for a value in this BST, in order to find it, we're going to ask ourselves the question, let's say we're looking for 12, we would ask ourselves the question, is 12 greater than or less than 10? And if it's greater than 10, we're going to go to the right. And here we only have 15, so there is no 12, so we're going to say it's not in our tree, but it is in our tree. It's just to the left. So having 12 to the left breaks the search ability in our BST, which basically makes our BST useless, which is why we say that 12 would actually have to be on this right subtree somewhere. So what this means is that right now, if we go through this function, we'll skip this first case. Let's say t is this 10 up here right now. So if t.left doesn't equal null and t.left.val is greater than t.val, then we return false. This isn't true, so we're just going to skip this. Same way, this also isn't true, so we're going to skip this. And now we're going to recurse down here, and then we're going to go into this node first, t.left. So again, 3 is less than 5 and 12 is greater than 5. So both of these checks are going to not return true. So we're going to keep going and then we're going to end up returning true and saying that this is a BST even though it's not. So the kind of general example, if you can't with something else, there's a million different ways to exemplify this. This method fails whenever a grandchild or great-grandchild, any like further child, has a value that is too high or too low, since the method only compares parents and children. So broken is BST would return true for this given tree, even though it isn't actually a BST. So let's try to fix it. In this case, we are given this function. This is an isBST function that calls this helper function. And here, if you notice, we have a min and max value. So make sure you make use of that when you are constructing this helper function in order to determine whether it is a BST or not. Okay, let's go over it. So first of all, when we call this helper function, we're going to start with our root naturally, and there is no minimum or maximum value for the root because the root's kind of arbitrary. So we're going to set the minimum value to be integer.minValue and integer.maxValue. Now the key here is that when we go over to the left-hand side of the tree, we know the maximum value on the left is going to be whatever the value of the root is, and the opposite is true for the right-hand side of the tree, where the minimum value is whatever that root value is. And that kind of idea continues on with the subtrees. So first we have this kind of sort of base case where if T is null, then it is a BST, because an empty BST is a BST. This is also handy as a base case so that when we hit a leaf, we can immediately say, okay, well, we've hit the bottom and we haven't found any contradiction, so this must be a BST. So we're going to use the min and the max just like we did. It was very similar to the structure of the 2a function. However, in this case, instead of comparing it to the value of its parent, we're going to compare it to the value of the min and the max that we are going to be passing in. And then here, what we're going to do is we are going to recall this function recursively. And like I said, we're going to update the min and max values appropriately. So for the left-hand side, if we're going to the left, we know that whatever values to the left of our current node have to have a maximum value that is, or have to be at most the value of our current node. So we're setting the max to t.val. And on the right-hand side, it's the opposite, where the minimum value is now t.val. We are passing down the min and max values from the previous recursive call for the other value, because for instance, if we go from the root down to its left child and then to the right child of that left child, like we did in the previous problem, then in that case, the maximum value is going to be the root and the minimum value is going to be that node's immediate parent. And that's it. That's all it takes. Okay, let's get into a game tree problem. So I'll give you guys a minute to try filling out the game tree with alpha-beta pruning, and then we will go over it together. Okay, let's go over it. So let's start with our alpha and beta values. So we don't have any value for this maximizer node. We don't have a minimizer node. So right now our alpha value is -infinity because any number at all is going to be better than what we currently have for a maximizer. And our beta value is +infinity for the same reason for our minimizer. So we pass that down until we finally hit an actual number. So now this number gets moved up into this maximizer node and our alpha value gets updated. So any value that is between 3 and infinity is going to be more likely to end up at the root than what we currently have. That's a lot of different numbers. There's a lot of options. So we have to look at this other child. And we're right, it is better. So we have the 7 that gets passed up to this maximizer. And then currently this minimizer has a value of +infinity. So we're going to replace that with 7. And now we're going to pass down a situation where the alpha is -infinity because, again, all we care about is the path to the root. So this maximizer is irrelevant. What we care about is the maximizer up here and the minimizer right here because we're caring about the how likely a number is to make it from this leaf all the way up to this root value. So currently, any number between -infinity and 7 is going to make it past this minimizer up to the root. So we go down, and we have our first number. So we have 10 being passed up. And so this maximizer is 10, and this minimizer is 7. So what this means is that whatever number comes out of this maximizer is going to be greater than or equal to 10, because it'll replace 10 only if the number is larger. And whatever number makes it past this minimizer has to be less than or equal to 7. Now, are there any numbers that are both greater than 10 and less than 7? No, right? That's impossible. There are no numbers like that are equal to that, which means that it's physically impossible for any of the numbers, even if we didn't know what these were, to make it up this tree, right? Because what would happen is that 11 would make it past this maximizer, but it would get stuck because 11 is bigger than 7 at this minimizer. And 4 wouldn't make it past the maximizer in the first place. So we can prune these branches. We don't even have to calculate what happens down there because it's irrelevant. It doesn't matter. So we're done with this whole subtree. So we're just going to pass up the 7 from the minimizer into this root. And now we start off with an alpha value of 7 because we need a number greater than 7 to replace the value we currently have as this maximum value. And we're going to go down the tree all the way like we did last time. And this time we hit a 2, so the 2 goes up here. Remember, we want to find the greatest maximizer on the path to the root. So even though there are 2 maximizers, we're going to pick the one with the larger number. Why? Because let's say we have a number like 5. Well, 5 would get past this maximizer, but it won't get past this maximizer. So it doesn't really matter whether or not it gets past this maximizer in the first place. So we need a number between 7 and infinity. That's lots of numbers. We do have to check to see whether this number is better. It isn't, so it's not going to make its way all the way up, but it doesn't really matter for now. So we have this 5 right here, and we have, again, a situation where we need a number that is greater than 7 in order to replace the number we have in this maximizer node, but is also less than 5 in order to make it past this minimizer node. Now, again, are there numbers that are both greater than 7 and less than 5? No. So we can prune this whole branch and not even worry about it, because no matter what comes out of this branch, it's not going to change the value at the end. So that's it. We can cut this whole branch off. We don't have to calculate any of the values, and that makes our life easier. So now you can kind of see why alpha-beta pruning is great. Even on a tree of this relatively smaller scale, it's really useful. And when we get into really, really big trees like you're going to do for project 2, you'll see that you'll get to save on a lot of computation time by doing stuff like this. Okay, let's do our last problem. So this is an extra problem. We want to print some paths such that it prints out all of the root to leaf paths whose values sum to k. So I'll give you a chance to try this out, and then we will go over it together. Okay, let's go over it. So, first of all, we have to figure out what this call is. Well, we're going to start with our root, as always, and our k is just going to be the k that we pass in, and our path at the beginning is empty because we don't have anything in it yet. So that's going to be our initial call of this helper function. So first, we're going to have our sort of base case / the last thing that kind of ends it or ends up printing out the path. So if we hit a leaf, that's what this is doing. If t.left equals null and t.right equals null, and k is equal to t.val, then we can just print out. And why are we checking if k is equal to t.val? Well, because as we do these recursive calls, the way we're going to handle keeping track of whether the path sums to k is by subtracting the value of the current path from k as we go. Because there isn't like a second argument that allows us to sum anything, so we're just going to keep subtracting for k, and if at the end k equals 0 / k equals t.val, then we can print out the path that we came up with. Now, otherwise, we're going to just need to add to the path normally, so we're just going to add t.val and then like a space between it and the next value. And if the left path is not null, then we are going to pass in the left value. Like I said, we're going to subtract the current t.val from k, and we're going to pass in the path. Same thing with the right side. We're going to do, if the right side isn't null, then we are going to pass in k minus t.val and then the path that we are building on. Now, in the case that the leaf doesn't some decay, it's not going to hit this if case, and both of these if cases are going to return false because we're on a leaf. So we're just going to return without doing anything. And that's it. That's our sum paths. Well, I hope you guys had a good time, and I'll see you guys next week. Bye.